back to this guy. We have one last special case that we're going to discuss. We last time talked about what about when A and B, D, E, and F were all 0, and all you have, or I'm sorry, not F, but when you're left with something like this, CX y plus F equals 0, and we said, well, that is the same thing as this guy. And we said, you know what, why don't we just call it constant K? And we said that could be solved like that. And we saw that very interesting thing happened. We ended up with these new things called asymptotes. That is, the graph of this thing approaches something but never actually gets there. Pretty much everything we've talked about up until now, like especially anything that goes off to infinity, it goes off in like both directions, right? This is something new. This is something that's approaching a specific value. This never, like when we were drawing parabolas and stuff, something like this would mean that it would go off in this direction forever, going over and over. That's not what's happening right now. We have something called an asymptote. And in this special case right here, the x-axis was an asymptote and the y-axis was an asymptote. One more time, that means that the graph approaches these values but never actually gets there, no matter how big of a value you put in. So that's just a review of what we talked about last time. To finish this up now, the last type of thing that we're going to deal with is the special case where C is equal to 0, which we've talked about before, but then we said there's a special case of the special case, and that is the following. And it's where the values A and B have different signs. Now, given something like this, and you've seen this in your homework now a bunch of times, you can complete the square and collect all of the values over on all the constant values over on one side, and finally divide through to obtain something that looks like this. X minus h squared over a squared. You have a y minus k squared over b squared equal to 1. And in the case of the hyperbola, in the case of the ellipse, what we've been doing now is that both of these values were positive. The a and the b value were positive. Hyperbolas occur where they are different. One's positive and one's negative. So you have a plus that and a minus this, or the other way around. The first one's negative and this one's positive. And so that's what we're going to be talking about today. Now, one other thing we didn't really talk about, when you collect all this stuff over here, what if that number is negative? And so, in other words, we have another case that we're not really discussing. So let's knock it out right now so that we don't have to talk about it. Let's suppose that you do all of this stuff, but the number you ended up with over here was a negative number, so that when you divided everything through, you ended up with a negative. There's a few possibilities. And right now, I'm not going to worry about the x minus h and the y minus k right now. This is just in general what you would get if you took something like this and completed the square and eventually you would end up with something like that. What we're going to be talking about are these guys here. X squared over a squared. Y squared over b squared equals 1. And then there's the question of the signs. Plus, minus, plus, or I should say minus plus, that's what we're doing. And then what about that guy? So suppose that this thing is a negative number. Now, like I said, I want to knock this out. So can I erase this stuff over here?
Yep.
Okay. Well, there's a few possibilities. Now, if these had the same sign and this were negative, check out what might happen. If this were negative, negative x squared over a squared, and this were negative, negative y squared over b squared, and you had a negative over here, well, you'd say, wait a second, I want to make my life a little bit easier and just multiply through everybody by -1. Multiplying by a -1 over here comes out to be a +1. Multiplying here by -1 makes the negative positive. Multiplying over here by -1 makes the negative positive, and lo and behold, I would have an ellipse, right? We're back to what we've been doing for the last however long, right? No real surprises there. What if, though, that were positive and that were negative and that were -1? Well, what we're going to be talking about is in the form where this thing is equal to +1. Same thing like with an ellipse. It's like I did a bunch of stuff and now I have it all equal to 7. Well, we're going to get rid of the 7 because it's going to make our lives easier. And so same kind of thing here, like you get down to this point right here where you have plus x squared over a squared minus y squared over b squared equals -1. You say, well, let's get it in the form that we want. I need to turn that into a +1, so I'll make everybody negative. And you end up with this plus, right? You're basically just flipping the signs. You can think about that as dividing everybody through by -1 if you want. I think about it as just flipping the signs. Anytime you have an equation, you could just flip the signs of everything and it stays true. And so it's another case where you end up with a -1 and, well, you just flip the signs. Ditto if you ended up with a -1, but your minus was first and then you had a positive. You'd say, wait a second, -1, I don't want a -1. Multiply through by -1, that makes this one negative and that one positive. And so you'd have that right there. So ultimately, what we're talking about now. So that, in case you're wondering why did I go on that little rant right there, it's because in your homework, you might end up with something that looks like this. And you go, wait a second, it needs to be equal to 1, right? Like, I just want to clear up any possible confusion that may happen. And so really anytime, and you'll notice that anytime these numbers here are different, right? Where if that's a positive and that's a negative, well, then you're always going to end up within this scenario right here. You'll see that in the homework. It'll be pretty obvious, but that's just something to notice. Like you could tell right away if you have something like this, for instance, 2x squared, how about -3y squared plus x minus 7y equals 0? You could look right away and say, well, hold up. There's a negative number right here. So that when I go to complete the square, ultimately, this is going to look like 2x blah, 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 minus 3y blah, 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 blah. And you can imagine, okay, I'll go through and do all the stuff. That's going to be negative no matter what. You can't get rid of it. You have a positive and a negative. And so, okay, that's the only way to make that work. Okay. So that's what we're addressing right now. That's what this is all about. There's one more thing, because you might be wondering. What's that?
I thought you were going to erase that.
Oh, no. One more thing you might be wondering about is what if these are both negative? Because I said they had to be opposite signs. And we know what happens when they're both positive and it's equal to +1. Then that's an ellipse. That's what we've been doing. What if they're both negative and they equal +1? Let's look at that. Let's just real quick, let's get that out of the way. X squared over a squared. So minus x squared over a squared minus y squared over b squared equals +1. First off, well, I could say And you'd say, well, that's the form you want because you want a 1 on the right-hand side. But what I'm about to do is the exact opposite of that. I'm going to say, well, let's multiply everybody through by -1 and see what happens. That makes this a positive number. That makes this a positive number. And now that's a -1. And so let's say that I wanted to find where does that go through the y-axis. And so I'd say, well, set x equal to 0. And so when x equals 0, that thing goes away and you have y squared over b squared equals -1. In other words, y squared is equal to -b squared. B squared is always, always, always a positive number. And so -b squared is always, always going to be a negative number. And so you go to find the intercepts and you have the square root of a negative number. That is an imaginary number. And so it doesn't go through there. This does not work in the real, the real plane, which is what we're dealing with. We're saying that we're taking real numbers x and real numbers y that we're plugging in. This does not work. And you can see that the same thing would be the case if we found the x-intercepts. We'd plug a y in and you'd have a -1. You'd go through and you'd end up with an imaginary number, which is not the game we're playing right now. We're not dealing with imaginary numbers. The only inputs for x and y that we are dealing with are real numbers. And so this case right here where they're both negative, it's not a conic section, and I doubt you'll ever deal with that. So long story short, the only thing that's left to do with this bad equation right here is to figure out when you have opposite signs for this guy. Okay, we good to go? Can we move on?
Yeah.
Okay, so it wasn't strictly necessary to talk about that stuff. It's just in case you were wondering, and it's good. I think it's good to be complete. So a hyperbola is what happens when you have this form, but the signs are different. So let's take a look at a hyperbola. And should we do? Yeah, we'll do actual numbers. And we'll say that the sign is different. And so we're in this scenario right here. Okay, now, what are the x-intercepts for this guy? I'm trying to graph it. In order to find x-intercepts, I plug in what for what?
Plug in 0 for y.
Okay, so let's plug in a 0 for y, and I'm going to do that. I plug in a 0 here. That makes that entire thing go to 0. And so now he's gone. I don't even need to think about him. And so it goes through the x-axis where?
Let's see. At 2.
And?
-2.
Yeah, there's no difference between this as of right now. There's no difference between what we've been doing and what we're doing now, right? Like once we're here, this is the same thing as if that were a plus, right? And we'd say, where does it go through the x-axis? Well, cover that guy up. Oh, 2 and -2, right? Because we would do this and we would have x squared equals 2 squared. Take a square root, you get a positive and a negative, and so you get plus and minus 2. So, okay, cool. Let's find what are the y-intercepts. How do I find a y-intercept? What do I plug in for what?
Plug in 0 for x.
Plug in a 0 for x. So when x is equal to 0, this equation reduces down to this. And What are my y-intercepts?
Hold on. Mm. Y would equal, or y squared would equal -9.
Okay, what?
Y squared would equal -9 or -9 or -3 squared.
So that
Y equals ±3. 3i.
Yeah, it would be plus or minus 3i. But I is nowhere on here because, like I said before, X we're only taking real values of X. We're only taking real values of Y. And so this is nowhere on this picture. Sure, he exists. If you like imaginary numbers, we could say, yeah, it's 3i, we'll make it work. But that's nowhere on here, what we're trying to draw. So what this tells us is that this thing, whatever it is, does not go through the y-axis. And so, does that sound familiar? Remember when we did this thing earlier, this type of hyperbola? It's a special case of a hyperbola. It had the property that it didn't go through the y-axis. It approached the y-axis asymptotically and did like that also down there. The thing is, the interesting thing about this is now this was a special case where the y-axis and the x-axis happen to be asymptotes. Those are not the asymptotes of this thing here. So like you might be tempted to say, oh, okay, so then it doesn't go through the y-axis, so it must approach y asymptotically. In other words, it must get close and close to the y-axis. It turns out it doesn't at all. It gets nowhere near the y-axis. This thing, we're going to see in a minute, what this thing looks like is this. It comes up like that, goes down like this. It also comes up and over like this, goes down like this. And the asymptotes that it approaches actually come from the origin out like this. There are two lines. One's like this.
Oh gosh.
The other is like this. And we will find the equations of these lines. And that's what you're going to be doing. And so now one thing to notice is look at this. This picture, if you take this and you rotated it 45 degrees, well, it's not quite 45 degrees because these things aren't, but imagining that this were perfect, that I've drawn it perfectly, if we rotated it this way, we would end up with this picture right here. If we took those axes and rotated it, right? If I took that one and rotated it up towards Y, then this thing would be like that. And that thing would be like that, right? These were my old points right here, there at 2. Rotate it, would end up here. This one down at -2, if we rotated it, it would be down there. This special case, the one that came from the XY, turns out is the more general case, this guy, but he's just been rotated up like that. So something interesting to know, but at any rate, you will deal with these, but we're going to kind of forget about them for right now. Just wanted to make that connection. And what we're going to see right now are that these, we want to describe what these asymptotes are. And I'm sorry, but so wait, just finally, just to make sure that I made another point, since we ended up, check this out, the negative was on the y, which means that if you were to try to find the y-intercept, you'd end up with an imaginary number, which means in our picture that this thing, this hyperbola, never touches the y-axis. Okay, that is going to be very helpful. And we could, by analogy, then say, well, if it were the other way around, if this were positive and that one were negative, then it should be the case that when I go to solve it and find where it goes through the x-axis, I'd end up with an imaginary number, which means that this thing would not go through the x-axis. We're going to see that in a minute. But I want to finish up this example right here, because the last thing to do, like whenever these again are the vertices, we're not going to get into it, but there's also a focus right here. There's a focus here and a focus here. We're not going to worry about the foci. There's a nifty little formula if you want to find them. Cool, have at it. And these objects are defined by their foci, given 2 points. We want to describe the set of points that are the difference between, don't even worry about this. The difference between the distance to the 2 points and a point on the thing is the same. And so kind of like with an ellipse, we took 2 points and said the sum of the distances is the same, and you end up with an ellipse. You have distance 1, distance 2. We say that the sum of these 2 distances is constant. Here we have a distance from one focus, we'll call that distance 2, a distance to another focus, distance 1. Instead of the sum of them being the same, it's that the absolute value of their difference is constant. And the thing you end up with is a hyperbola. Like I said, we're not going to worry about that. You could even start with this definition and derive this. I did that yesterday just to make sure that I could, but we're not going to worry about that. We could do that in this class. We were running out of time, and so we're not going to bother with it. The important thing, though, is that we can recognize, given something like this with opposite signs, as of right now, we could say if the negative is on the y, then it's this type of thing. It comes through at some point or 2 points that we could find, and it goes out like this and down like this. And we're about to find what these asymptotes are. Okay. Questions so far?
Not yet.
Not yet? Okay, cool. So that's the name of the game right now. To finish this picture off, because I didn't really say this, what I'm trying to do is, given something like this, graph it. And so what did I do? I found the intercepts. That's always going to be step 1, or find really the vertices. And that's given by this. The only difference is with the minus there, we don't have anything going through the y, and so we know that that guy goes out that way. Now we need to find the asymptotes. This is not going to be a very convincing argument. I know, because it wasn't convincing for me when I first saw it. And with a little bit of calculus, it becomes very convincing. But without calculus, it's kind of one of those hand wavy things that your teacher says, and then you just plug into your mind is like, okay, this is dogma. This is how I find an asymptote. But let's look at this. This thing right here, we can consider this branch right here as a function. In fact, if I could solve for y, if I get y by itself, you're right, buddy. I could see maybe, and this is the idea, maybe if I get y by itself and consider this one thing right here as a function, then I could find the value that this thing is getting closer and closer to. Well, let's just see. Let's take this equation and solve it for y. And so a few different ways we could do this. I mean, the minus is right there. So I'm going to think about this as bringing this over to the right-hand side. And so I'm going to add y squared over 3 squared to both sides. That gives me this guy right here. That 1 is hanging out. Let's get the 1 on the other side. So I should have x squared over 2 squared minus 1 equals y squared over 3 squared. And it's like, I don't like that 3 squared in the denominator. I'm trying to get the y by itself. So why don't I multiply both sides of this equation by, how about 3 squared? Okay, so I do that. 3 squared. 3 squared. Okay, that gives me my y squared, which is nice. I'm going to go ahead and distribute this in. A few different ways of doing this. I'm going to do it this way. 3 squared. No, actually, no. No, I'm not. I wanted to do it this way. And this is what's really unconvincing about this is I'm going to do something that you probably haven't seen before and whatever. But here's the idea. Okay, I'm going to say, well, wait a second. It'd be nice if I could get rid of that guy. If I could factor him out. And so what I'm going to do is just straight up factor this guy out. How do I do that? Well, I would need to have a 2 squared right here. Can you do that? Can you do that? Well, yeah, because think about this, right? Like this is the same thing as 3 squared times 1 over 2 squared times x squared minus 2 squared. And if you distributed this back into here, you would have, oh yeah, x squared over 2 squared. Yeah, okay. Distribute that guy back into here, and you would have minus 2 squared over 2 squared. And yeah, it would come back out to 1. So, all right, I guess it works. It looks really funky. And this will be one of your best friends in calculus, being able to do this, factor something out of a denominator. But that's how it works. And that's, believe it or not, this is the same thing as that right there. I'm just going to double check it. Yep. The 3 and the 2 would come back in. Yep. 2 would come back in and be over that. Yeah. Okay. It's the same thing. The whole reason I did that was to set this up. So now that when I take a square root, I have one number that's sticking out front, which is nice. So I'm going to take a square root of both sides. Taking the square root of both sides gives me a positive and a minus. And so I have y equals plus or minus all that stuff, the square root of all that stuff. And the whole reason I pulled that that I pulled that 2 squared out is because, well, now I could rewrite this, the square root of something squared, over something squared times some other stuff. I could rewrite that as the square root times the square root, right? In other words, this is plus or minus the square root of 3 squared over 2 squared times the square root of x squared minus 2 squared, like that, which I could simplify. And that's the idea here. So I'm going to bring this back up right here. Okay, y equals plus or minus 3/2 times the square root of x squared minus 2 squared. There we go. Okay, what does that do for me? Well, let's look at this. We just found the upward part of this right here. And the downward part, the y plus 3/2 times the square root of x squared minus 2 squared right there. This part down here would be the y equals minus 3/2 times the square root of x squared minus 2 squared. It's kind of how that works. We break it into a positive and a negative. That's what we do when we take the plus and the minus. Now we could kind of see what's happening here. And this is the really unconvincing part about this argument, is that when x gets really, really, really large. Now, take a second here, because remember what we did when we were talking about asymptotes with y equals 1 over x? We said, what happens when x gets really, really, really large? Well, the value gets smaller and smaller, right? When x is 100, you're at 1 over 100. When x is 1,000,000, you're at 1 over 1,000,000. You're getting closer and closer to this. So to find an asymptote, the idea is to imagine these limiting cases, like when x gets really, 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 really big. And the thing to notice here is that when x does get really, really, really big, x squared is way bigger than 4, right? Like we're taking the square root of x squared minus 4. And when you're at like 3 squared minus 4, well, 9 and 4 are about the same size. But when you're plugging in like 1,000,000 squared is like a million. It's like it's a trillion or something. Trillion minus 4, it's basically a trillion, right? Like plug in 5 trillion into there and then square it, and you have a number that has, 20 some odd zeros. Minus 4, that's not much, right? And in fact, we could say, and this is the idea, when x is large, this is the type of thing you talk about in calculus. The idea I'm bringing up here is a limit, which you'll learn, but the idea is that when x is very, very, very big, then x squared minus 4 is about the same thing as x squared. Does that make sense? Like, take 5 and square it. Okay, that's 25. Minus 4 is 21. That's pretty close. Like 25 and 21, that's a pretty big difference between 25 and 21. Mm-hmm. But take 1,000,000 and square it. Or rather, let's just take 100 and square it. 100 squared is 100 squared minus 4. 100 squared would be a 1 with 4 zeros after it. 1, 2, 3, 4, I believe. Minus 4. That's 9996. That's very, very close to 100 squared, which is 10,000. 9,996 is very close to 10,000. And the difference gets even smaller the bigger you get. Like if I plugged in, say, 1,000,000, 1,000,000 squared minus 4. Well, 1,000,000 squared would be a 1 with 12 zeros after it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Minus 4 would be 999,999,999,996. And let's just look at that. 9,999,999,996 is very close to 1,000,000 squared. So that's kind of what we're saying here. When x gets really, really big, this 4 doesn't matter. You're minusing off just a tiny, tiny fraction of what that thing is. And so we could say then, okay, when x gets really, really big, you could basically forget that that minus 2 squared is there. And so what does that give you? Well, let's see. So did you follow that little line of reasoning right there?
Yes, I did.
Okay, good. So I'm gonna get rid of all that. And basically, we're just comparing sizes of stuff. And we're noticing that here, as we get bigger and bigger, because that's what we're trying to figure out, long-term behavior. Just like we were trying to find long-term behavior of 1 over x, we just imagine plug in a gigantic number. Well, that's what we're going to do. Plug in a gigantic number, and then if you minus 4 off of it, it's not going to matter. So we could say then it's very, very close to plus or minus 3/2 times the square root of x squared. It's as though that minus 4 isn't even there. But the square root of x squared is just x. And so then as y gets very, very large, this thing is very close to plus or minus 3/2 x, which is a line right there. And it happens to be that line, the asymptote right there. That asymptote has the equation y equals 3/2 x. This one right here is the negative part of that, right? Because we had the positive and the negative when we took the square root. And so the bottom one down here, as this gets really, really, really large, this thing gets closer and closer to y equals negative 3/2 x. And we could do some extra argumentation to show that the same is true over here, that these are indeed the same lines. All I was working with were the positive parts. It comes from the fact that this is squared, and so you could plug in negative numbers, but we're not really going to get into that. You just, if you don't believe it, we could go into it more, but I think it's pretty obvious from the graph of this thing that this has to be the same line. Nothing funky is going to happen over here. Nothing funky is going to happen over here. We didn't talk about symmetry. You could show that this is symmetric across the y-axis very easily, actually, but we didn't talk about it. But at any rate, that's the idea. This line right here that this thing approaches as it gets bigger is given by that. Now, we don't have to do this every single time. The same way that, like, once we got our ellipse in the form x squared over a squared plus y squared over b squared equals 1, we were just able to say, oh, it goes through at plus and minus a. Oh, it goes through at plus and minus b. Well, the same thing happens here. The line that this approaches happens to be y equals that number over that number right there. Why? Well, because you would go and you would solve this and you would go through all this, blah, 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 blah. And in every single case, you're going to end up with whatever b is here, because right, it's over b squared. It ends up, the b is on the top and the a is on the bottom. No matter what numbers you have there, no matter how crazy they look, that's how it ends up. So you could think about that as a formula for the asymptotes. And so, and it doesn't matter what the signs are in this case. So can I erase this picture right here?
Yes.
Okay, so that gives us a bit more information that we could go ahead and say is that if we have something like this, as long as the signs are different, then the asymptotes, totes are y equals plus and minus, because we have two asymptotes, right? The one that's coming up and the one that's coming down, plus and minus b over a. So whatever the, and you could just imagine like, wait, how do I keep this straight? Well, you bring the y to one side and you do some magic. The b would come up into the numerator. The a with the x would stay in the denominator. And then you'd have the x squared and blah, 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 blah. But in the long run, that will approach that line right there. And so that's a nifty little formula. I don't remember the formula. What I remember is, well, wait a second, get the y on one side. Oh yeah, and the b would come up. And so you'd end up with something like that. And then there's some crap about pulling something out of a square root and blah, 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 blah. But that's why that's the case. Okay. And so that picture that I just drew, that I just erased, would be all that we need to do for that. We've labeled the asymptotes. We labeled where it went through the x-axis. I think that's it, really. That's all there is to that. Now, let's make it hard. Okay, can I get rid of all this stuff?
Yep.
Okay, so now let's do, well, I think it's called the conjugate of this. Is it called? Yeah, it's a conjugate. The conjugate of this is where you just flip the signs. That one's negative, that one's positive, and it's still equal to 1. Let's take a look at that guy. What are the y-intercepts? How do I find a y-intercept?
Set x equals 0.
Set x equal to 0. So we set x equal to 0. That makes that go away. We get y squared over 3 squared equals 1, which means that y equals what and what?
Plus or minus 3.
Plus or minus 3. And so, right, like in the same way as before, I could really stop using my brain, right? Just like with an ellipse, I kind of get it now. Like once you have it in this form, that's why we have that form, so that you could just cover up the negative one and say, well, it must go through the y at plus or minus whatever that number is. And so we go up to 3, we go down to minus 3. We'll label those points. And now I know this is an ellipse. I mean, I know this is a hyperbola because of the opposite signs. And so I know that this thing is, well, we don't really know that yet, but it's the same reasoning. This thing now is going to go up this way, like this, and it's going to come down this way, like that. And guess what? The asymptotes, just like I said, are going to be exactly the same. Why? Well, let's just be clear about this. Let's look at what would happen. Oh, by the way, does it go through the x-axis? Is there an x-intercept?
No.
Don't look at my picture. No. How do you know that? The negative is on the x. If you tried to find an x-intercept, you would plug in y equals 0, and you'd say, okay, well, now I have this equation, and I'd have a negative x and a 2 and blah, blah, blah. And you would find that it should be plus or minus 2i. And you'd go, wait, we can't do that here on the real plane. So we'd say, whoever, and then the lesson to take away is that whoever has the negative, if the x has the negative, he don't go through the x-axis. If the y is the one with the negative, then he don't go through the y-axis. So that's the idea. Now, finally, to find the asymptotes, we could just use our equation and say plus or minus 3 over 2 is the lines that it goes through. But let's just really, I really want to show why that's the case. The idea is that we're solving for y. We're getting y by himself. And so I'll keep y on this side this time because he's already positive. I'm going to bring the x squared over by adding x squared over 2 squared to both sides. Now I have a plus 1. I multiply through by 3 squared. And I do that nifty little trick where I pull out the 2 squared, which would put a 2 squared up in the numerator like that. Just double check it. The 2 comes back in and we'd end up with that. The 2 comes back in, we end up with 1. Yes, okay, so that's the same thing as that. And when I take a square root, I get a positive and a negative answer. Taking the square root pulls that guy out as 3/2. times the square root of x squared plus, we'll just write it as 4. And again, the idea is when 4 gets really, really, really big, when it's a very, when x gets really, really, really big, he's way bigger than 4, right? And so it's as though this thing, as x gets large, we can write it as this, as x tends to infinity in both directions, whether it goes in the positive direction or the negative direction, won't matter. This thing, the y value, will approach plus or minus 3/2 square root of x squared, which is y equals plus or minus 3/2 times x, which is a line. And it happens to be the same line. The one with the positive slope does this, and we're going to label it as y equals 3/2 x. The negative one comes down like this, and we'll label him as y equals negative 3/2 x. And there's my hyperbola. So really, it doesn't matter which one's positive and which one's negative. The y is always, the y value, the b value for the y always ends up in the numerator for the asymptote. And the a always ends up in the denominator for the asymptote. And so there we go. That's why when you inevitably forget this, you could say, well, wait a second, if I were to solve it, blah, 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 and you have that stupid thing with the square root. Oh, that's right. The b ends up in the numerator, the a stays in the denominator, and I'm left with that guy right there. So that's the idea. That's why it works. Now, everything else is very straightforward. In fact, it's exactly what you've been doing. The only thing that's left to do is if there is a shift right or left in the x or the y, or in the x, we'll shift it right or left. The y will shift it up and down. And that's really easy with this thing, because now instead of trying to keep track of 4 points, we're only keeping track of 2 points. And then you just move them this way and this way. The hard part is, what does that do to my lines? Because the lines also have to move along with the picture. But we could use the same reasoning that we've been using all along with this stuff right here. It's like, so let's do an example of something similar. So okay, so we'll do an example. Can I get rid of all this stuff?
Yep.
Okay, so fine. Here is an example. We're going to go x minus 1 quantity squared over 2 squared minus y plus 3 squared over 5 squared equals 1. Step 1, let's find the, just like with the ellipse, we're going to pretend that this thing hasn't been stretched, or I'm sorry, has not been shifted left, right, up, and down first. And we're just going to look at this, the case where if it were x squared over 2 squared minus y squared over 5 squared, what would I have? Well, this goes through one of the axes. Where does it, which axis does it go through, and where does it go through it?
It goes through the x-axis.
Where and where?
2 and minus 2.
There you go. 2 and minus 2. Okay. Now it's good to go ahead and draw the asymptotes first. I don't care what it ultimately looks like. And so if every pair of asymptotes you draw are exactly, square like that, like I won't mind, although it's good to do it this way. So let's find the asymptotes, and we could imagine that, yeah, we're moving the y and the x, and ultimately whatever's in the denominator of the y is going to show up in the numerator. we're going to end up with a plus and minus. Whatever's in the denominator of the x is going to stay in the denominator. And so what's my slope?
5/2.
5/2. There you go. 5/2x. And so my asymptotes for this guy who hasn't been shifted is just going to be whatever goes with the y on top, whatever goes with the x on the bottom. We have 5/2. So plus and minus 5/2. So I'm going to kind of draw that somewhat accurately. I'm going to draw him kind of steep like this. Label that one as y equals plus 5/2 x. We'll draw the other one steep just to be somewhat more accurate. Like that. And so that's going to be y equals negative 5/2 x, just like that. Now I'm going to go through and draw my hyperbola, showing that it is approaching these things, and it looks pretty bad, but whatever. That's the idea. Now the only thing left to do is the shift. Okay, so the shift in the x direction moves them 1 unit to the right. The shift in the y direction moves them 3 units down. And so I'm going to go ahead and just imagine that. Like I take my, oh, that should be a +2. +2 -2. Moving him over to the left by 1. And another thing we could do, but it'll be nice, is to think of where the center is going to be. There's that center point, which when we haven't shifted anything was always the origin. Moving him 1 unit to the right would be here at 1. 3 units down would be here at -3. There's that. Now it's kind of, so I imagine that's where that x went. That x is going to come down like that. We'll find those in just a second. Now, the 2 got shifted over 1 unit to 3. Sorry about that. The positive 2 got shifted over to 3 and down to -3. So he's down here at 3, -3. I'm not going to, I don't care if you do it like that or do it on the axes, that's fine. This guy went from -2 over 1 unit to the right to -1 and down to 3. So he's here at -1, -3 right there. These guys look like that. Now all that remains, well, got to find intercepts, but all that remains now for the asymptotes is just to shift it. And all we got to do is just use these principles that we've been using all along. If I want to shift, so we have a function y equals 5/2 x. And if I want to shift it right or left, I mess with the x value. And so I could say, well, then that's going to be 5/2 to shift him. Buddy, just get out of it. He's stuck. Just go backwards. So, in fact, it's going to be the same direction, right? Like this would be this function shifted over 1 unit because I subtracted from the x value. Now, there's 2 ways of doing the next step. You could say, well, then you've gone down 3 units. So subtract from, and we're just talking about a line here. How do you bring a line down 3 units? You just subtract from the actual value. It used to be the case that its y-intercept was 0. Now its y-intercept should be 3 units below. You could just say, okay, then that should just bring you down minus 3 units, just like that. Its new y-intercept is here at minus 3. No, not necessarily, but yeah, anyway, you know what we're going to see here in a second. You just take the whole thing and shift it down. Another way of doing this, though, is look at how we wrote this. We could have added, and this is, I'm running out of room. I'm going to take this guy right here. Y equals 5/2 x minus 1 minus 3. And that is indeed that guy right there. Well, what if I added 3 to both sides? In other words, look at what that did. Considering these both as inputs, right? Which is weird with lines I know, but look at that. Y plus 3 and y plus 3. Oh, interesting. X minus 1 and x minus 1. They both do the exact same thing. In one case, I did it this way, where we think, okay, if I need to shift a function right or left, I play with the input, which is what I did here. And if I want to shift a function up or down, I play with the output, which is what I did right here. I said, take this line and shift it down another 3 units. But that's the exact same thing as if I had added to that guy on that side, which is kind of what we've been doing here, right? So however you want to do this, ultimately, what we should end up with is, and you could write this in either way that you want. You could write it as y equals 5/2 x minus 1 minus 3. And then the other one is, well, it's the same exact thing. It started off at minus 5/2x, and we needed to shift it 2 units to the right. So I subtract from here. And so we're starting there with minus 5/2 x. And so minus 5/2 x minus 1. And then I would have minus 5/2 x minus 1. I could go minus 3, or I could add to the input. If thinking about y as an input, right? Thinking about it in parentheses, either way you want to do it, doesn't matter. The final bit right here is y equals negative 5/2 x minus 1 minus 3, or you could have written it as y plus 3 equals minus 5/2 x minus 1. And yet another way, just to kind of wrap this up, another way you could think about all of this is if you said, well, what if at the very beginning of this problem, if instead of calling this x squared and y squared, you know, when I first started saying, pretend it hasn't been shifted at all, what if I use completely different variables to begin with? What if I had said, how about u and v? We're going to pretend this is u squared and v squared. Well, then this wouldn't be x and y. This would be a u. This would be a v. That would be a u and a v. U and a v. This would be a u and a v. And then in this last step with these asymptotes, we just said, well, hold up, u is actually equal to x minus 1. We just did a nifty little math trick where I said, pretend that this x minus 1 is actually u. And so in the end, instead of 5/2 u, I would have 5/2 x minus 1, which is, that's what I have. And I didn't do it over here, but finally in the last step, we'd say, well, instead of minus 5/2 u equals v, well, u is just x minus 1, so I just replace it right there. The v, we said at the very beginning, is y plus 3, and so that's where my v comes up. And so that's kind of nice if you want to think about it that way right there. But that's ultimately what you're doing, and I wanted to show these 2 ways of thinking about this to show like they're really the same thing, and either way you want to go about getting to that, they mean the exact same thing. So Okay. That's what you're going to be doing. The only thing that we're not doing right now, because we're completely out of time, is that we would need to find these values right here. I could tell from my graph that it goes through the x-axis. Still doesn't go through the y-axis. We didn't bring it over far enough to go through the y. So the only thing I'm going to check is to find the x-intercepts. X-intercepts happen where y is equal to 0. And that's precisely what you've been doing with ellipses. The only difference is that's a minus sign and not a plus sign. Any question?
Okay.
Any question?
Not yet.
Okay. I know, like, as you start doing these, you're probably going to run into stuff that's crazy. Although, let's see. Your book does a decent job of this. They are not too, they do that stupid thing. Well, yeah. They do a pretty good job of explaining. Sure do they? They barely go into that. Yeah, I don't know. I think the hardest thing to wrap your head around is this part with the asymptotes. But hopefully after doing a few of them, you'll get into the swing of it. So, okay. Can I erase this and give you your homework?
Yes.
Okay. Homework. This is section 4. Page 450. And it's almost exactly the same as your previous homework. We're going to start with 1 through 19 odd. Then I would have assigned 21. The problem is that they tell you to find a hyperbola using, and they give you the foci, which we did not talk about, so we're not going to do that. So we're going to do, in lieu of that, we're going to do 22, where they tell you to find a hyperbola, but they've given you the asymptotes instead, which we have enough info for that. It's not really that hard. It's kind of the same kind of thing. And after having constructed a bunch of them, now you're just going in the reverse order. It's like, if I know the asymptotes, well, then I know what the A and the B value were. And so I could reconstruct that kind of stuff. There's one more thing I wanted to say. I'm not recalling what it was. 23, yeah, 23. Is pretty much what we just talked about. It's talking about like the examples we did. It had X over something minus Y over something. And then we did it where it was the minus X and the plus Y and stuff. The only difference from what we did in here and the actual homework problem is that instead of 2 squared and 3 squared, they're using A squared and B squared. But the conclusion should be the same and so on and so forth. So all this and the redo number 19 from last. And don't do intercepts or foci.
Okay.